Okay, so now we are moving back to the normal textbook. So the last unit was kind of making sure we had the microeconomic fundamentals to start talking economically about sustainability. And so that's what we start to see in this first chapter, chapter 2. Um, Make sure you're reading chapter 2 and start reading chapter 3. So this is lecture C1. So chapter 2 is going to kind of be like this lecture and the next one, and then we'll start into chapter 3 for the lecture after that one. I will get some additional Canvas activities out there, and as I add more Canvas activities, I'll also sort of start trickling in more drops so that it doesn't feel like there's, so you can help sort of planning the workout, you know, for the future there. I want you to be able to have practice time, but I also don't want you to feel overburdened by it. But I'm working on that, and then the next homework as well, I'm working on that. So those will hopefully be released sometime soon. In the meanwhile, are there any questions about the materials so far after lecture B5A or lecture size, where we did all the stuff where we kind of ended in calculating consumer surplus and PED? Anything in particular before we getting into new stuff?
I have a question regarding the the B5 homework.
Okay.
It's about the answering, no, the like the way you answer the questions. Do we have like some sort of, do we answer it in like a Word document, or what do we do exactly to upload the answers?
Thanks for asking that question. It just has to be readable, legible. You have to keep in mind that the TA that's grading these has to grade a lot of them. And if she can't find your answer or read your answer, then it's likely to kind of be marked off. So you kind of have to imagine, like, if you're submitting this, I mean, it's not quite a professional document, it's a homework exercise, but you have to kind of think that you want to write it for the reader and not for you. And so just kind of make sure you've composed things so that they kind of make sense. Probably put answers towards the end. It's great if you have arrows and things that are circled. It's even better if you can manage to put them in a digital format, because you're not going to be submitting a lot of handwritten stuff after you leave school. So it's good to practice that. And so that is kind of like the preference, but it's totally fine if you want to do it handwritten. You just need to make sure that as you do it, it's legible and clear and composed and put together, structured in a way that's easy for the TA to find your answer and grade your work. That makes sense.
All right, thank you.
Mm-hmm. I see a question in the chat. We'll be able to go over a few more examples of what goods are inelastic and elastic based on the lecture size. So I mean, so I don't know that originally planned for today, but we certainly can I can try to come up with some on the spot, or maybe I'll do this. In the chat, could people put in an example of what they think is don't give me a definition, but can you come up with an example of a good that you can think of that you think is an elastic good? And let's just sort of survey what people think in the chat. So let's look for at least a few of those in the chat. So what do you think? So my question is give an example of an elastic good in terms of price elasticity of demand. So, and then as you're filling in answers, I'm just going to remind people that these are goods for which, if you have a change in price, you're going to get a change in quantity demanded. People will be responsive to changes in price. So any other thoughts about that? What, I'm looking at the samples coming in, but any other samples that are coming in here, what you think are things that people respond to price, they're elastic. I can see a lot of interesting answers here. Great things that we can chat about here. So, so I'll just pick a couple kind of randomly here. So, energy drinks and then types of beverages. So 2 beverage things came up there, and that's kind of interesting. So can somebody give me an example of why they would think that beverages would be elastic goods? I like the answer, and I have my reasoning, but I'd like to hear maybe somebody else's reasoning or see somebody else's reasoning. If you've got like a phrase or whatever, you can put in the chat. Any thoughts for why energy drinks would be elastic goods, or drinks in general?
Because it's a want, not a need.
It's a want, not a need. I like that. I like that. I also see some answer that kind of going right along with that. I kind of like more economically phrased one, lots of substitutes available. So I really love the answer. It's a want, not a need. Now we can say, how do we make that economics? Like, what would an economist, how would they say that? What does it mean to be a want, not a need? It means that there are a lot of other substitutes available, and I might want one thing, but if I can't really afford it, or it's a little too pricey, I might buy another thing. I can always drink water. You know, so you could say like, man, I really like that kiwi acai refresher or whatever thing. But you look at it and say, I'm not really willing to pay $4 for a drink that's mainly filled with ice. So I'm really thirsty right now. I'm just going to get a cup of water. So, but if somebody says, oh, it's only $1 today, then you can say, oh, well, for $1, I'm willing to buy it. So that is an example when there are lots of substitutes available, then it is elastic. You're very responsive to price. Now, I've seen some other examples in here that I would have probably been into the other area for inelastic. So, so there's some other things here like, you know, so like electricity, for example. So here's one that when it kind of depends on the price of electricity. So that's the beauty of PED. If you remember the PED formula, which you know, it's, you know, relative, so, you know, it's percent change in quantity divided percent change in price. Or I can maybe, you know, write on the, I'll use the PowerPoint here too. Oh, that was not. So change to a pen. So if you remember that PED is the relative is really important here. So maybe the reason why I think electricity is inelastic, but you think it's elastic, depends on you know, our context. And so like, you know, if you think about delta Q over your, so how much are you going to change your consumption relative to your current consumption compared to how much did the price change relative to its previous change? And so for me, when I think of electricity as being cheap. So the price is small. And so if they change the price, they could make a huge change in the price, but it wouldn't actually be a large absolute change of price. So like off peak, I think SRP charges 7 cents a kilowatt hour. And so off peak, you know, after 9 p.m., if they were to double the price of electricity, would go to 14 cents a kilowatt hour. That's a big change, but it's not that much per kilowatt hour. You know, an electric vehicle, for example, if you had an electric vehicle, the entire 300 miles that you would associate with the electric vehicle would be about 75 kilowatt hours. So, you know, 75 kilowatt hours times 7 cents is, I don't know, like $5 or something like that. So, you know, 300 miles, that might be all that you drive in a month, especially this month. And so, you know, that, you know, it's relatively cheap. And the quantity of electricity, you know, well, actually, as much as I use electricity, I don't actually use like that much of it. It's not like something that that I can imagine myself, I don't feel constrained by my electricity use. Now, for if I did use a lot of electricity, like you know, if I was running if I was doing a lot of Bitcoin mining or something like that, well then that is going to use so much electricity that that if they increase the price of electricity, I might not get enough out of the mining process to justify that, and I would be very responsive to that change in price. So electricity, I think at normal levels, I would view as inelastic because you don't, the prices are relatively low. You don't necessarily notice them, and you don't kind of use enough to feel that constrained by it. So they can increase the price and you probably won't notice. If anything, you might have a little less available to spend on other things, but your price that you spend on that won't change that much. So that's the reason why I would view price as inelastic. But there are certainly scenarios where if you were spending a lot of your budget on electricity, then it might become much more elastic to you. So brand name foods is another one that brand name foods to me are something that I would view as inelastic, because if, well, okay, actually, let me take that back. When the answer brand name foods came up there, I saw brand name. Usually when I see brand name, that is a heuristic to me that somebody is looking for that brand. And if you have to buy that brand, regardless of everything else, then it's inelastic. But now when I look at brand name foods, then I think, oh wait, actually maybe the reason why brand name foods is brought up when I asked for elastic goods is you thought there are generic foods I could be buying instead. And that's a perfect example that actually, in the terms of brand name foods, I'd say, yes, those are elastic. If you raise the price of, I don't know, raise the price of bread on a brand name bread, then I will just go off and buy Fry's bread instead. I'll go buy in the grocery brand bread. So that's a great example, actually. Brand name foods is a great example because there are so many alternatives. Brand name electronics is a little less, because brand name electronics, those people might, that's more inelastic, because you're like saying, I really like Apple products, and so I'm going to buy Apple products even though I could buy an Android phone. I really like Apple products, so I'm going to buy the iPhone regardless of what price the iPhone is. That's an inelastic good. Okay. Gasoline is another one of those that it depends. I mean, I think it depends on people's income. I think a lot of people who make enough money don't think about the price of gas at all. But I think a lot of people who make less money do think about the price of gas, and that might cause them to say, take public transit. So if you have a lot of money, you just pay whatever the gas bill is. You don't care what the price of gasoline is. But if you don't have as much money, then maybe as you go from $2 a gallon to $3 a gallon to $4 a gallon, you start asking yourself, can I just ride my bike instead? Can I take a bus? You know, that sort of thing. So in that case, gasoline can be elastic for some, and then inelastic for others. And so that is going to, and the difference there isn't a change in the formula. The difference there is the change in the demand curves. My demand curve for gasoline at my level in my career might be different than your demand curve for gasoline at your level of your career. And that's, so we would shape those demand curves differently. So if you, for any price you buy the same quantity, then that's going to generally be inelastic. For, on the other hand, if you basically are willing to buy any quantity at like a single price, it's a little flatter than that, then that's going to be very elastic. So you're very responsive to changes in price. All right. So does that help? Does anybody else need more examples of what we mean by elastic and inelastic goods? Great. Thank you for the question. All right, so let's do a little more. You know, we're going to start out with a little bit of review here, and we've got our demand curve. And on one axis of the demand curve is some quantity of a commodity or good. It's a good if more of it means better. If the generic term for this that I sometimes have used is commodity. A commodity is just a physical thing that you can buy. And then on the other axis, we have the price per unit of that good. And so now that we have this demand curve, the demand curve represents how much you value a good, how much you are willing to pay for a good. And you have to think about that in terms of how much you already have with that good. And so the idea here is that if you have none of that good, so you're currently own 0, then the demand curve kind of tells you how much you might be willing to pay to get to 1 unit of the good. So if I don't have any of the good, I'm willing to pay the most to get it. And another way to view that is if I have none of the good, then I get the most value out of the first unit of the good that I get. So it's how much am I going to benefit from the good? And that's always going to be, for these goods of diminishing marginal returns, that's going to be largest when you have none of the goods and you buy one of the goods, then I get the most out of that, that first good that I buy. So a term that we're going to use in this chapter and on is the marginal benefit of the good. So marginal just means like, you know, like it's on the margin. So I've had this much and I want to decide if I want to add a little bit to it. So that marginal increment, you know, on the margins, on the side, that little bit of extra, given how much you currently own, you can think of that as the x-axis is kind of how much you currently own. How much would you pay for the next one? That's what we mean by the marginal benefit. How much would you benefit from the next one? So if I were to charge you $40, but you're willing to pay 100, then you would be willing to buy that from me, but you're not going to get $100 of benefit out of it because you had to give me $40 of benefit. So that's $40 you could have spent on other things. So due to opportunity cost, then the $40 that you give me means that it kind of takes $40 of joy away from the $100 of joy that that one unit brings you. And so all you're left with is the 60 here. So the marginal net benefit is going to be 60 for this first unit of the good, first unit of the commodity. And so as you can see, as we move on, then as you buy more and more, these marginal net benefits eventually go to zero. And the spot where they go to zero is going to be the utility maximizing quantity. So that spot right there, that is the spot where you are not willing to buy. You're not willing to, or I guess the price of the good is equal to your value of the good. And so it's an equal exchange. And so you might as well just keep your money. So that's what happens. That's why you buy up to 40 or up to the quantity equal to 30. You buy to the point where the value of the next one is equal to the price on the market. And so what you own and how it benefits you is this area underneath here. And so that is the total net benefit. So that quantity, if you were to buy less, so let's say instead I bought, 20 or something like that, then what you're doing is you're leaving benefit on the table. So if you bought 20 of this thing, then you'd say, but you know what? I still get more out of buying more of them than they cost in terms of their price. And that's why your existing benefit is kind of what's accumulated behind how much you already own. And there's new benefit that you could add. And so because of that, you are going to then buy more. Now on the flip side of that, if you owned more than this amount, then the price of the good, you can think of it keep going this way. At that point, the price of the good is larger than the benefit. So this is the benefit you get from that good, and this is the price that you get from that unit of the good. And at that point, you're paying more than you got out. And so you would do better by not owning that much, by backing off, selling those, for example, getting your money back if you can, and getting back to this level. So that's the utility maximizing level right there. And this is rephrasing the equimarginal principle that we have already seen. So the equimarginal principle before was that your marginal rate of substitution is equal to the price ratio in the market. Well, the equimarginal principle for a single good can be rephrased as saying the marginal benefits of the good are equal to their marginal costs. So the dollar of benefit per the next good, that's like your benefit, is equal to the dollar of cost for buying the next good. So this again is exactly the equimarginal principle we've already talked about. It's just been rephrased in terms of a single good. So this is the new version of the equimarginal principle. And so utility maximization is a statement that saying that people maximize utility is saying that they choose quantities of goods that maximize this area, which we refer to as the consumer surplus. And the consumer surplus is another way of saying the benefit that an individual person gets from owning a stock of something. Or we can scale that up to society level And we can view this as the benefit to society for, let's say, a good being a particular price. And so we're saying that if we can make a good cheaper, we're going to bring more benefit to society because more people will afford it. There's a question, is consumer surplus and net benefit the same? Then I would say that yes, consumer surplus and net benefit is the same. The area underneath this curve is the same as the difference between the gross benefit and the cost. So in the chapter, basically this thing here is equivalent to benefit at level X minus cost at level X. And that just happens to be occur where marginal benefit is equal to marginal cost. And that's the equimarginal principle. And so this demand curve, we're going to now be referring to as the marginal benefit curve. And the price of a good, we're going to refer to as the marginal cost of the good. And so where marginal cost equals marginal benefit is where you maximize consumer surplus, which is also where you maximize net benefit, which I'll circle here, net benefit. Net NB, net benefit, or total net benefit maybe. Total net benefit, TNB. All right, any questions about that? Here, I'll just go, I've got another slide that's just for questions. Any questions about that? All right, so the real reason I have this slide here is we have phrased so much so far in terms of goods. It is just easier to think about goods, but we need, for sustainability purposes, ways to find economic frameworks to think about things like pollution. So the question is, how the heck do we think about pollution? Now, I have introduced ways for you to put bads on Pareto frontiers and things like that. And I think everybody agrees, it's hard to think about the combination of a good and a bad together. It's hard to think about the combination of a bad and a bad together. The first question on your homework is about thinking in a Pareto sense, or actually it's thinking in an indifference curve sense about two bads. And hopefully you'll be able to work through that. And I think it'll be a good exercise to work through that. But at the end of the day, I hope you agree that it's just easier to think about goods with goods, not goods with bads or bads with bads. And so we need a way to come up with a framework where we can think about pollution in terms of goods, as opposed to thinking about pollution in terms of bads. Pollution is a bad. If you get more pollution, you have, it's bad. You do not want more pollution. By definition, you want less pollution. You are better off in a world with less pollution. That doesn't mean you can eliminate pollution, but you're better off in a world with less of it. So what do we do? So how do we deal with the fact that pollution is a bad? We want to be able to model bads, but we also want to be able to only use goods. We want to be able to model pollution. We want to do it in a way that only uses goods. What concept do we invoke that helps us turn pollution somehow into a good? This was a question on the. Great, yeah, I'm seeing answers come in there. Abatement. So hopefully this is a term that you've seen in your other classes. If not, that's fine, but you should become familiar with it. The term abatement is an economic term that just represents the ending, reduction, or lessening of something. So the clever thing that economists do is, instead of thinking about pollution as a bad, they flip the axes around and they say an infinite amount of pollution is a zero amount of abatement, and an infinite amount of abatement is a zero level of pollution. So they just, again, they flip the whole axis around in this weird way where infinity is mapped to zeros. And so infinite pollution is zero abatement, infinite abatement is zero pollution. And by doing that, then it provides us a framework where we can think about pollution using all of the tools we have about thinking about goods. Because now we're not thinking about pollution, we're thinking about pollution control. We're thinking about pollution abatement. And so we can then ask ourselves, how do the benefits to society increase as the amount of pollution control, as the amount of abatement increases? And so that's what we're kind of plotting here. How do benefits increase with increasing amounts of, say, sulfur dioxide abatement? So down here, where abatement is equal to 0, then that's kind of a baseline where we're saying there's no pollution control. There's just sulfur dioxide being emitted with absolutely no constraints. It's just uncontrolled. That's, you know, abatement. Zero abatement is zero controlled. That is the uncontrolled case. And so if you view that as your baseline, as we're swimming in a sea of sulfur dioxide, that is our baseline. And then we can say, all right, if we were to add a little bit of control, then how does the benefit change? So we know that it'll go up because abatement is a good. Abatement is a good. And so as you get more abatement, you know that the benefits must go up. So we know that this has got to be shaped in this kind of increasing slope because it's a good. But we don't know exactly where it's going to go up to. So as you increase abatement, then how do we know that it's going to be steeper here and shallower over here? And so that's really the question, is then, you know, why this shape? You know, why is it shaped in this concave way? So from the perspective of the x-axis, you can view this as a cave. And so this is, we're going to call this concave. And a rationale for this is that you tend to do the cheapest and easiest and kind of low-hanging fruit things first. And so typically, like you could say, you know, there are usually easy things you could do that for the cost of them, which is super cheap, you get lots of benefit out from. And so, you know, initially there are, you know, you can eliminate waste in your factory. So your factory is eliminating, you know, emitting a lot of sulfur dioxide. And you look around and you say, you know, you left that machine on for way longer than you needed to. It is cheap for you to go and turn that machine off. And it may cost, you know, another minute of your employee's time, but that extra minute you pay the employee to go and shut the machine off is going to benefit society by reducing the amount of pollution you're putting into the air. So down here, these are the cheap abatement strategies. And they bring the kind of the largest amount of marginal benefit. So I'm going to say large marginal benefit. So for every little bit you do, you get a large impact of that. Again, just turning machines off. Now, eventually you're going to get to the point where your factory is super, super efficient. Machines are turned off, lights are turned off, there is no waste anywhere. And at that point, the only way you can reduce your sulfur dioxide emissions is to pay for sophisticated chemical systems that you're gonna have to install somewhere. They're gonna scrub these things. These things cost a lot of money and they wring out just a very tiny amount of pollution. And so to get that extra little bit of pollution, it takes a lot of extra work. It's the same thing with cleaning your house. You know, there are a bunch of quick things you can do to make a major impact on, you know, just like pick up the cardboard box that you unpacked or whatever and put it in the recycling bin. That's an easy thing to do. But when you really want to get, like, you know, your sink shining, it's going to actually take you really scrubbing that thing. And so at those points, like, you know, are you going to really, like, if a visitor comes to your house, are they going to notice whether your sink is a little duller? Probably not. But you had to put a lot of effort into getting that shine on there. They will notice if there's a big cardboard box in the middle of your living room. I mean, that's an easy thing to take care of. You just put it in the recycling bin and you're done. So the easy things often have the largest marginal benefit, but we run out of them and then we're left with the hard things. And the hard things are going to be expensive and they are going to have small benefit. And so there's small marginal benefit up here. And that is the reason why we often have concave utility functions for things like abatement. Okay. Does that make sense, the shape of this? Are there questions about that? All right. Now, I have been referring to things being cheap and things being more expensive, but I'm kind of getting ahead of myself. At this point, when you think about a benefit curve, I do not want you thinking about the costs of that curve. I want you thinking just about the benefits of that curve. So I did happen to order things where I said the cheapest thing are the things you do first, but think of them more as the things you do first. And so if I were to increase my level of abatement, I'm going to first do a certain set of things and then do other set of things when I need more abatement. I am going to clean out the cardboard boxes first, and then I'm going to wash the sink second. And so that is not an actual reference to the costs of it. And so the benefits that we see here are meant to be perspectives of what we have, just the raw benefits regardless of their costs. And those benefits are often going to be concave. And that's just because you tend to do the things that have the biggest impact first, and you tend to do the things that have the smallest impact later. And that tends to be because of the cost. But for regardless of worrying about the costs, I don't want you confusing this curve with a cost curve. The cost is a separate curve, and that's what we're introducing next. So does that make sense to everybody? That we sort things by kind of, so this abatement curve, like you'd say like, okay, I understand tons of sulfur dioxide, but I don't quite understand this abatement axis. Like, how do we know what goes where on the axis? Because if I'm not doing anything, there's a million things I could do first. And you have to ask yourself, well, yeah, but what are you actually going to do first? And if in the case of sulfur dioxide, you're not going to install the scrubbers first. You're going to tell people to turn off the machines first. So that's how we're ordering things on this axis. Any questions about that? All right, so then that allows us to say, okay, but then now let's actually bring in the costs. And so these costs, I can ask the same thing, why this shape? Typically these cost shapes have this shape, and this shape is convex. You can think of this as being outside of a cave, and since it's outside of a cave, it's not concave, it's not with cave, it's next to cave, and so it's convex. And so this convex shape is typically the shape you see for these cost curves. And we could say, well, why is that the case? And we've already kind of talked about that. It's because of how we order the way that we do abatement. You will typically order abatement, so you will do the cheapest abatement things first. And so those are going to be the ones that are kind of lower in cost. And as you get to higher levels of abatement, you will start doing things that are increasingly costly, more and more costly for the same kind of unit of abatement. So in order to get one more unit, one more ton of pollution out of the air, you're going to spend a lot more money. And so that's why they're typically this shape. So we have to combine those two things together to figure out the optimal abatement level. And the optimal abatement level is the one that maximizes the benefits to society. And so how do we measure benefit? The total benefit, the net benefit, is just the subtraction of whatever benefit I get of the abatement minus however much I had to spend on it. And so at this point, it looks like there's a lot of benefit there. But if I get a little more abatement, then I actually get a little more benefit, because I'm still at a point where the benefit curve is rising faster than the cost curve. So I hope you can see that here, is that if we think of this kind of football shaped thing, then the benefit curves are initially rising faster than the cost curves. And that means I get a spreading out where I end up getting, it's better to do more up to a point. And that point happens to be this point right here, because at any points to the right of this, then I end up getting a contraction of these. And so to the right of this, then I can see that my benefit curve rises more slowly than my cost curve. And because of that, the cost catches up to the benefit, and the total benefits kind of decrease. So typically, economists would say that this is the utility maximizing. This is where you want to be. This is the level of abatement. You could spend more money on extra abatement, and it would make things better. But the amount of cost that you would have to put into making these better may itself put you at worse off. Like, let's say that in order to get, a ton more sulfur dioxide out of the air, you had to take money away from other efforts that were, say, cleaning the drinking water. And so now I've taken cost away, or money, you know, opportunity costs, I've taken money away from the other things in order to just make sulfur dioxide better. So if we have just a singular focus on sulfur dioxide, and that's all that matters, then maybe we just do as much as we can. But in reality, these costs matter. We have to spend money on other things as well. And so we need to say, what's the right balance of these things? And economists would say that you stop your level of abatement at this point. Even though you could do more, the amount that you could do more could probably be better used doing something else. Okay. And so now we can say, all right, how do we mathematically characterize this so that if someone gives me these curves, I can actually calculate a number for them to say, go out and spend this much on your abatement. And if you think about if you go back to kind of calculus here, maybe if you go back to calculus, you can say that, well, this here inside this, is my benefit. This is my total net benefit. And if you remember back to calculus, how do you maximize things? Well, you set their derivatives equal to 0. So if I want to say, well, what's my quantity of abatement that maximizes my total net benefit? I would just take the derivative of the total net benefit with respect to quantity and set it equal to 0. And so we're not going to have to do a lot of this calculus in this class, but I want to see where this comes from. Is that then I were to then work this problem, then it turns out that would be equivalent to taking the derivative of the benefit curve and subtracting the derivative of the cost curve. And I hope you can see here, this is just my way of writing mathematically that same property that I showed you graphically a second ago here, where this slope is the derivative of the benefits curve, and this slope was my attempt to try to make the derivative of the cost curve at roughly the same quantity. So for this quantity here, I can see that this derivative is very high, it's a very steep slope, and this derivative is very low, it's a very slow slope. And this, and the difference between these derivatives ends up, that difference will be equal to 0 when I'm at the utility maximizing quantity. And so that is what I'm going to look for, is the quantity Q of abatement that brings my derivatives equal to each other. And so again, I'll just showing that graphically there. And this region, my derivative of the benefits is greater than my derivative of the costs, which means I should increase my quantity. In the other region, the derivative of the benefits is less than the derivative of the cost. The cost has a steeper slope, and so I should decrease my quantity. And then so finally, in this region, they're parallel. So these two lines, the derivative of the benefit and the derivative of the costs, are parallel to each other. The derivatives are equal. And so this is another type of equimarginal principle that we have here. And so the utility maximizing level is where the marginal benefit is equal to the marginal cost. That's an alternative way to say that, is that economists don't like the word derivative. I don't know why. I think it's because in stocks, we have things called derivatives. So instead of saying derivative, economists say marginal. So when the economist says to you marginal benefit, then what they really mean is the derivative of the benefit curve. When they say marginal cost, they mean the derivative of the cost curve. And so where the marginal benefits equal the marginal costs, that's the equimarginal principle, and that maximizes the utility to society. And so what I will do is I can plot the marginal benefits. So that's this blue line up here. This is the marginal benefits curve. And I can plot the marginal cost curve. And so this, if you like, is the derivative of those two bendy curves, the convex and the concave one that we just had there. I just took their derivatives. And what we see if we plot their derivatives is that one of them starts high, that's the marginal benefit curve, and it falls. The other one starts low, that's the marginal cost curve, and it rises. And they intersect at exactly the point where we have our utility maximizing level of abatement. And so this should look familiar to you. This should look like a demand curve. And that's what we're kind of getting into here. All right, so before we go on with further geometric interpretations, are there questions about that?
I got a question.
Yep.
So you said that this looks like the demand curve. These lines are just essentially the derivatives of the marginal benefit and marginal cost, right?
The marginal benefit curve is the derivative of the benefit curve. So it's not the derivative of the marginal benefit. The marginal benefit is the derivative. So it's not that we're not taking derivatives of marginals. The marginal benefit is another name for the derivative. So marginal benefit means derivative of the benefit.
Oh, okay. Thank you.
So I could maybe put little equal signs here. Marginal benefit equals that, and marginal cost equals that. All right, any other questions? This will end up being a shorter lecture than usual, I think, and so there's plenty of time for questions if any of this is not so clear so far. Okay. And like I was saying, this blue line should look to you like a demand curve. And so all of the stuff that we have been talking about so far is effectively going to be stuff about marginal benefits. And so you can view the marginal benefit curve as kind of a willingness to pay for one more unit of abatement. So given that we've paid for this many units of abatement, then the blue line tells us that we're willing to pay this much for the next unit of abatement. That's how much we value the next unit of abatement. And it just so happens that the cost we have to pay is going to be equal to that. And for any higher levels of abatement, more than that. And so we end up saying, well, I don't get enough benefit out to justify the costs. And that's why this ends up being the level of abatement that we choose. Okay. So moving forward with this, then we can say that the area between these two curves is the net benefit curve. So the area between these two curves, if I were to go back to any of these slides with the curvy lines, so let's say, I'll go back to this one. The length of this distance here, this is between the benefit. So if I were to color that in and say, the length of that line. So if I were to maybe draw a little line over here and a line here, and I'll put little arrows saying this is a distance. And so that corresponds to that point, and that one corresponds to that point. And this here is just the benefit of this quantity of abatement minus the cost of this quantity of abatement. That length right there, which you can put in units of dollars, that length in the marginal curve, so if I go ahead to the marginal line here, which is this one, is equal to the green area here. So if you were to take this area here, and so you think about it, this axis is in price per quantity. And so this axis is in quantity. So the area here is in units of dollars. It's in units of price. And so the area here, the area of that triangle, is equal to the length of that line between benefit and cost. So that is just an alternate way of finding the same thing. If you've got the convex and the concave benefit and cost curves, then if you measure the length of the line between them, then that is going to be exactly the same as if you measured this triangle area right here. And that's the net benefit to society. The area there. Okay. Questions about that? And just to kind of like, so if I were to summarize this entire lecture so far, it would be this slide, where marginal means derivative. That's something you should have in your head, is that economists don't like the term derivative. They don't say the derivative with respect to quantity. They don't say anything like that. They don't even write D. They don't say dQdt or dQdP or anything like that. Economists prefer to write M for marginal. And what they mean by marginal is the derivative of whatever they're saying is, you know, marginal benefit, the derivative benefit with respect to your variable of interest, which is like quantity, how much quantity that you are increasing, how much benefit you get per unit quantity. So marginal means derivative. And so with respect to that, the equimarginal condition up here, that is actually saying that the derivative of the benefit curve is equal to the derivative of the cost curve. But a lot of times we're just going to plot those marginal benefit curves raw. We're not going to actually go and show the real benefit curve. We just end up plotting the derivative of the benefit curve. And the marginal benefit curve is analogous to the demand curve that we built up to last time. It is how much you're willing to pay for this quantity of whatever, in this case, abatement. And then there's going to be a cost associated with it, and those costs are typically going to rise. And the area between marginal benefit and marginal cost is the net benefit. So if you were to buy a different quantity, let's say this quantity here, then you would get rid of the triangle to the right of that line, and you'd only have the area of the trapezoid to the left of that line, and that would be the net benefit at this level. But the net benefit at the utility maximizing level is the full triangle. And if you were to then do more abatement, then you do get an additional triangle out here. But this is kind of the funny thing to think about. The triangle on the right area is negative. And so as you cross into the triangle on the right, you're actually taking away benefit. So the area on the left is accumulated benefit. The area on the right, after the cross, is reduced benefit. Okay. So questions on this area interpretation of benefits and costs? Okay. All right, and then driving home the demand point is that this marginal benefit curve is just a demand curve. And so demand represents how much a person or market values a good, and marginal benefit plays the same role. It's so for every unit of a good, how much do you value? How much would you be willing to pay for another unit? That's what the marginal benefit curve is. It's just the same thing as the demand curve. And if I were to write a benefit function up here, so this up here is a concave benefit function. If you were to go and ask, Wolfram Alpha or your calculator to plot that thing, it would end up looking concave. It would like do one of these things. And if you then do a little calculus, if you take the derivative of that thing with respect to q, then 10q minus q squared gives you 10 minus 2q. And then that will end up giving you a curve that looks just like this one over here, where you've got 10 on this axis, the choke price, if you will. And this slope here would have a slope of minus q. So for, minus 2. So for every unit you add, you decrease the marginal benefit by 2. And that's what's being plotted there. And so this marginal benefit function is basically an inverse demand function because it maps quantity back to marginal benefit, quantity to price. Any questions about this or the math behind this? Now we've talked about potential ways you can measure marginal benefit curves by asking people how much they'd be willing to pay. There's a question, are you going to be using a lot of calculus class? No. You'll be, all of the work that you'll have to do is going to be algebra, is going to, it's going to be looking at graphs and maybe doing a little bit of geometry, a little bit, tiny bit of geometry to form algebraic expressions. And most of those algebraic expressions, once you do that type of problem once, it'll be the exact same expression for all members of that family of problems. You just will have different numbers in it. The only reason I'm bringing up, showing you the calculus here is I just want to show you that there is, in theory, a map from something like a benefit curve to a marginal benefit curve. And that map happens to come through calculus. But in this class, am not going to give you a benefit curve and ask you to calculate the marginal benefit curve. I'll just probably give you the marginal benefit curve. But I want you to know behind the scenes that there are these things called gross benefits, or, and those benefits do relate to marginal benefits. And the precise way they do is a way that the calculus elegantly connects for us. So don't be afraid by the calculus. You're not going to be doing calculus. If you don't, I just tried to pick a relatively simple problem of taking a derivative of a polynomial, but you're not going to have to do that in this class. I think I might have put a question in the lecture size where you had to do something like that. But it's just once to kind of get you trying to remember a little bit of calculus you previously had and see that, try to get the gears moving again. But that's not the main focus of this class. It's just kind of a refresher. Any other questions, concerns? All right, and so I've mentioned how you can estimate marginal benefit by asking people, then how do you estimate marginal cost? And I really like this example that they gave in the textbook, which is how to estimate a marginal cost curve for, in this case, a conservation program. And so this is not an abatement example, this is a conservation example, so just as relevant to sustainability. And the way they get this marginal cost curve effectively is a way that they rank these options for conservation in terms of kind of what you would do first. And so if you think about it, you typically do, again, the cheapest options, and though it just happens to be that those cheapest interventions are not only pursued first, but if we were to plot the benefit curve, they typically have the most benefit as well. But if we're just focusing on cost, we can rank things by how much they cost. And so like here, we can say habitat protection, various low-lying areas. So that's pretty cheap, right? Because we don't have to do anything except rope something off, right? The habitat's already there. So all we need to do is prevent people from, encroaching on that habitat. And so the annual cost here, they're saying, is $4,000. And so we can convert that into condors saved per year. So if we know how many condors saved per year, then we can get this kind of like 0.53 condors saved per year, which we can then flip into dollars per condor saved. So effectively, what the economic question we're asking is, what is the utility maximizing level of condors to save? You can't save every condor, so how many condors do you save? You don't want to kill them all, that'd be bad. So somewhere in the middle, how do you determine that? And so what we can do is we can take habitat protection and turn that into dollars of condors saved. And it turns out habitat protection is a cheap way to save condors. So that is a great way. If you've got no condors, just protect some habitat, and suddenly you'll get condors. Super cheap. And so that's one of the first things that we do. And that's why the cost of that shows up as being very low. So going from no condors saved per year to say, whatever, 10 condors saved in a year is a pretty cheap thing to do via habitat protection. Well, then after that, you say, okay, we've protected as much habitat as we can. So now what? So then you say, well, okay, what's the next thing we can do? Well, the next easiest thing to do is reduce contaminants. So we know that condors are affected by these lead shotgun pellets that they end up ingesting. So we need to go out and clean and get rid of these things or stop people from using these things. Well, that's going to take a lot. That's a lot harder than roping off an area. So that's going to cost us $20,000. We can figure out how many condors that'll save. We can turn that into dollars per condor. And there you end up getting $30 per condor per year. So this is more expensive. And so it ends up being it shows up, here. So we were down, this first one showed up down here on the marginal cost curve. And this second one shows up over here, 30, the marginal cost curve. So we spend a little bit more to save the next increment of condors. And then we go on further and further. So, we can only do that so much. Eventually we clean up all the shotgun cells. There's not much more we can do with that. So now we have to actually start modifying things. Well, that's super expensive, modifying power lines and things. And eventually though, we can do that. If we really care about saving condors, we will do all of that. And then if there's still condors left to save, then the most thing that we can do is then step up law enforcement. And so that ends up being paying people to go out there and enforce our conservation policies is the most expensive thing we can do. And so that's like way over here. So if you really want to save, close to 4 condors per year, then you're probably going to need to do all of these things. You don't just do the enforcement. But you will have to step up law enforcement. And so there would be a marginal benefit curve that would be coming down this way here. And this would be the benefit of all of these things. And what we'll end up finding is that those two would intersect with each other. And then that kind of gives us a threshold for saying that this is the optimal number of condors that we can save per year. We could, in principle, spend on people going out and better enforcing the law, but that is so costly that the benefit that we realize, and however we're measuring benefit from condors saved, is not going to be worth the amount of cost we pay into it. And so we're going to be stuck conserving this many condors. Now, of course, if you can go out and find cheaper ways to save condors, that's great, we'll do it. So that tells us that the way we save more condors is maybe going out and finding cheaper intervention strategies, because people are not just going to volunteer to pay people to do these expensive things unless you either prove to them that the benefit of condors is much, much greater than they used to think, or you come up with something cheaper to do other than law enforcement that'll fit within what the benefit function that people already have. So remember that this demand curve relates to people's utility, how much they personally value condors. And so if you want people to spend money on expensive intervention strategies, you have to make it worth it to them. You have to increase their utility curves. You have to increase their demand curves. If you don't think you can change the way they look at condors, then you need to come up with cheaper ways to save condors. That's the message that we get here. All right. So any questions on the construction of this curve? Questions or comments? Does it make sense how this curve is structured? How if I gave you a bunch of different strategies and put them in terms of dollars per condor, so condor is the quantity here, that you would hopefully be able to sort them and place them in kind of a graph like this. Okay, pretty clear. All right. So that's all I'm kind of summarizing here, that our policies are sorted by cost per condor. So you can view the amount of condors you're saving, like how many things that you can end up saving a lot of condors per year through one method, but it's really costly. So it's going to show up on the far right of the marginal cost curve. Over here, there's a lot of cheap things you can do, but they don't save a lot of condors. And so they show up on the left side of the marginal cost curve. If you sort them all, you plot them all in this framework here, you get what tends to be this nice convex shape. And then that ends up providing you this marginal cost curve that we can end up kind of using to thinking about how decisions are made. All right, so any other questions? There's not really much more that I have for you today. So now is your chance. We are starting to move out of the qualitative part of the class into the more quantitative part of the class, where you're going to see a lot more functions being drawn, shapes being drawn, a few formulas. just solving things that require moving things from one side of an equation to another, dividing things out, stuff like that. And so we'll be, interpreting graphs in ways that are useful, and then applying math in ways to take those qualitative interpretations and turn them into quantitative recommendations. Okay. All right, so in that case, I think we're done. And so I'll give you an attendance question. So I'll put, for convenience, the URL in the chat as well. And so for today's attendance question, I want to say that I'm asking, what term do economists use instead of the term derivative? So I, as a mathematician, might say, well, it's the derivative of the benefits curve. And but that's not what an economist say. What would an economist say instead of the word derivative? What other term do economists use instead of derivative? And I'll put that in the chat as well. The question is, what term do economists use instead of the term for derivative? As in the derivative of the total benefit function. And otherwise, I'm happy to take any questions if you've got them. Otherwise, that's all I've got for you today. So if you've got nothing else, you can pop off, and I'll see you next week. Have a good weekend. As a reminder, I do have office hours today, Mondays and Thursdays at 4 p.m.
Thank you.
Thank you.
I'll see you next week.
Oh, you too.
Thanks so much.
Yep. All right, looks like people are rapidly heading out. So I am heading towards ending the meeting. So last chance. All right, bye all.